So Zigbee is one of the leading contenders for IoT. Every protocol is contending for IoT. Wi-Fi has its version for IoT. Bluetooth has its version for IoT, and Zigbee is another one for IoT. So while the other two, the Bluetooth and Wi-Fi, are general purpose, really, I mean, they were designed much before IoT happened. And Zigbee was also designed much before IoT happened, but Zigbee is trying to take that space because of its low power and things like that, right? And so we'll talk about Zigbee. Zigbee features, versions, device types, topologies, all that, and then we'll go into protocols and the applications. We will spend a lot of time on the networking layer, AODV and DSR. Okay. Now, AODV and DSR are actually not really related to Zigbee alone because they're used by other protocols as well, but they are good to know as a wireless routing person. And then we talk about Zigbee Smart Energy version 2. So Zigbee overview. So this is designed for industrial monitoring and control application. So much before IoT, before we had the word IoT in 2010, people were still needing some way for the industrial things to talk to each other. And things, I mean, those were really not things, those were controllers and devices, big things, right? And they need to talk to each other, so they could afford a lot better than what we are talking about now. So they're requiring a small amount of data, turned off most of the time, and like wireless light switches, meter reading, patient monitoring, all of these things can use Zigbee. Okay, ultra low power, low data rate, multi-year battery life, and that we have already seen. Power management to ensure low power consumption. So everybody sleeps all the time, like we saw a minute ago. And less complex, 32 kilobyte protocol stack versus 250 kilobyte for Bluetooth. What that means is the program size. If we were to implement a Bluetooth in a device, the program size would be 250 kilobyte. Okay, if you were to implement Zigbee, it's much simpler, 32 kilobyte, right? So your memory cost would be reduced. And the range is 1 to 100 meters up to 65,000 nodes. So you can have big network. Theoretically, I mean, if you have 65,000 nodes, I don't think anybody will be able to talk to anybody. So you really don't have that many, but that is theoretically possible. Tri-band, and it runs in 3 bands. You can run in 2.4 gigahertz, just like we saw, 16 channels are 5 megahertz each. We saw that in 15.4, right? It can also run at 915 megahertz, 10 channels. Now 915 megahertz has very small bandwidth, doesn't have 80 megahertz. It has few megahertz, right? That's why you only have 10 channels, and it doesn't say what is the channel size, but then you can get only 40 kilobits per second. The channel size is very small. Now, what is good about 915? Anybody can say anything? Why would you want to use 915 and not 2.4? What is good about a lower frequency? Right. So that's the idea. I mean, this is just a fundamental. By now, I have said it 10 times. That if you have a lower frequency, means longer wavelength, you can go farther with the same, everything else remaining the same, right? So that's why that is a good band. Is that if you want to go lower power and still go farther, you use 915. And 915 is not allowed in Europe. Okay, so they have 868. It's very similar. So everything that you implement, you just have to implement that both frequency are just limited to one market. When you go to Amazon and buy these things in that band, they will say whether it is 915 or 868. Don't buy the wrong thing in the wrong country. You can buy 868 in America, but the spectrum police can come and catch you. right? And so this is not legal in the United States. Similarly, 915 is not legal in Europe. Yes, it is seller doesn't care, and Amazon is universal, right? Global. People buy it from all the countries, everything, right? So you can end up buying wrong thing. Okay, but be careful. 915 ISM band is in the United States, and 868 is the corresponding band in Europe. And 868 also they gave you a smaller bandwidth, so it is only 20 kilobits over there. So zigbee. First of all, what is a zigbee, right? So zigbee, you know what is a bee, right? The bee that goes on flower to flower. And if the bees were not there, there won't be any fruits because they do the transfer of whatever is required from one flower to the next. Now, when they go to the food, they don't go straight line. They go like this. Okay, zigbee. So they go zigzag, right? So somebody noticed this and they just named it this protocol after that thing, that we are going like this to wherever you want to go to. Zigbee. All right, named after the zigzag dance of the honeybees. Direction of the dance indicates the location of the food. So they would be going like this, and you think that they're going in this direction, but not. They're going straight. Okay. So Zigbee. Now, it uses 802.15.4, which we discussed a minute ago, MAC and PHY, and the layers which are 3 and 4 are done by Zigbee Alliance. And they can have up to 254 devices or 64,516 simpler nodes. Now, this is all theoretical. Okay, you can have 65,000 or 64.5, whatever number devices. That is basically 2 raised to, let's see, 64 is 2 raised to 8 and 1000 is 2 raised to 18. So this is 2 raised to 18 devices, right? However, nobody is going to have that. This is just related to the 16-bit address. Okay, sorry, I calculated it wrong. 64 is 2 raised to 6 and 64,000 is 2 raised to 16. So because we have to give you a 16-bit address, I can't count more than 64,516. So I can't give the address. So this is really not that I would like to have that many children. I would not be able to manage. You see what I mean? So that is a theoretical limit. Generally 254 is a practical thing. Named after zigzag dance. I already said that. Multi-hop, ad hoc, mesh network. Now there are 3 words here. Multi-hop, ad hoc, mesh. Multi-hop means that you can send a message who is not next to you. So if we make a line here and I say, okay, I'm going to send the packet to you, please send it to, and let's say to Ria, right? Then you will send it to him and he will send it to Ria. That is a multi-hop. Because generally in Bluetooth and other simpler networks, you just send it directly either to the base station or directly, right? And in both cases, it is called single hop. Even though you're going through the base station, it is single hop. Huh? Yeah, right. Single hop means you cannot go if the hop is disconnected. But in multi-hop, you can probably try other path, right? So multi-hop, okay, that is one. Second thing is ad hoc. What does ad hoc mean? Ad hoc is the opposite of infrastructure. Infrastructure means you have to go and fit in something in the room before you can use it, right? That is the base station. So if you don't have a base station, that is ad hoc. Okay. Mesh. Now mesh has 2 meanings. Now this is very important. Please listen carefully because this is in the exam. Mesh routing and mesh topology. They are different. Topology is mesh means it looks like the one shown in the picture. Okay. It is not a tree. It is a mesh. right? And routing means you can send packets, you know, like this going around, right? Now, you don't have to have mesh routing with mesh topology. You could have straight routing, mesh topology is there, and then I could just be sending like this straight line. I mean, actually, I'll be sending a straight line, but I don't have to I don't have to discover. I could just say that, all right, even though I allow mesh topology, we will do tree routing. Okay, tree routing means we will somehow discover a tree inside that. That's what they do in Ethernet. In Ethernet, mesh connection is allowed. You can connect anything to anything, but they make a spanning tree, right? And in a spanning tree, there is no mesh routing. You just go to the root, and from the root, you go down to where you want to go to, right? So this is mesh routing and mesh topology. Understand the difference? Okay, so the question is, can you do mesh routing without a mesh topology? The answer is yes and no. Let me explain how it is. Is that suppose I am capable of doing mesh routing, okay, but the network is a straight line. I can work on that one, and I can still do so-called mesh routing. I'm not really doing anything, but I am capable of it, and I'm implementing whatever AOD. We will talk about mesh routing protocols. We can implement them on the network which are not mesh, although there is no advantage. So I can do mesh routing on a tree topology. All right, but there is no advantage. On the mesh topology, you don't need mesh routing either. Okay, you could do tree routing on the mesh topology, but really, if you want to use mesh topology, the best thing is to do mesh routing. Okay, so mesh topology is in general multi-hop routing. Mesh topology is in general multi-hop routing. Now, hold on. Now, for everything there are exceptions. So now think about a circle, like we are in this room right now, and we are connected in a circle. Now we could do multi-hop without going through mesh topology, right? Mesh routing. We could just do, like, I mean, basically. So there are many different combinations, possible here. I'm sorry. What was your question? Okay, so that's the thing. You said that mesh topology is the heart of. I don't know what heart of means. Huh? Part of multi-hop is one way. Let me just put it this way: one way to implement multi-hop routing, because you don't need mesh topology. I just said you can have a linear network, you can have a tree network, and you can do multi-hop. Okay, now again, the word best is an extreme. So the thing is, there are exceptions for everything, right? Yeah, I said that word mesh best myself, but I think if you didn't do mesh routing on a mesh topology, you might not get all possible benefits. Now, best is the thing is, this is a multi-dimensional optimization problem. So we are trying to optimize the power, we are trying to optimize the distance, we are trying to optimize bit rate, and so on and so forth. So you give up one on the other. There's a complexity. For mesh routing means you need a computer to store. You need the storage to store the thing like that. So yeah, you pay something, but then you get something. Okay, that's why I don't want to use the word best, but yeah, it's kind of related. Yeah. All right. Now that you understand those four words, we go to Zigbee Pro. So the Zigbee was 2004. Zigbee Pro came in 2007. So this is basically Zigbee version 2. And they added these new features. First of all, stochastic addressing. So before 2007, the addressing was that each one needs an allocation. Okay, let me tell you what it means. So let's say we have I'm the coordinator, and there are four full function devices. And then behind you, there are hundreds of reduced function devices. So I will give you, all right, you can give your children numbers from 1 through 10. You have 10 through 30, you have 30 to 500, you have 500 to 600, right? So you can have 100 children, you can have so many, you can have 10, right? And if so, the advantage was that I know exactly when somebody says, I want to go to children number 13, I know where it is because I have given the numbers, right? When you get the number from, let's say, 10 to 50, when you have full function devices behind you, you give them sub numbers. You can say, okay, like 50 to 60 is yours, 60 to 200 is yours. So everybody knows who is where. Right? At least you know their parents, and then parents know their children, and the children know their children. So the numbering was very, very strict and allocated from the center. That was good, easy, because then now we don't need memory to remember who is where. Otherwise, I have to keep a list of 1,000 nodes and their locations and who's their parents and how do I get there. However, that also caused problems. So what if I gave all my numbers with four children and now I have fifth children somehow who want to join? Where do I find the numbers? And I gave you four addresses and now you have fifth children, So this was a problem, right? So they said, no, 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 we cannot do that way. So they said stochastic addressing means we generate a random number and give it to your children. All right, that's what we do right now. Right now, when a child is born in a family, we don't have to ask anybody. We don't have to ask the government, what name can I give? You just give a name. You pick up a random name and give it to them. Right? The problem is now we cannot find them. And so we have to register somewhere. Okay, all right, I have a child named this, and then, so they will keep a whole list, big register. That's the thing. So device is assigned a random address and announced. Mechanism of address conflict resolution. So now here's the thing now. If random name is a problem, because suppose you gave somebody named Raj, and there is another Raj there, now what? Now we have trouble because we cannot use short name anymore. So they said, okay, all right. So as soon as you give a name, you announce to the whole network, not the world, to the whole network. And if somebody already has that name, that number, then you now draw another random number. Right? So this is how it is done. Parents don't need to maintain assigned address table. So because the address has been resolved means we have made sure that when I gave the name, there was nobody with that name. Yeah, right. All right. So there are two people who can find who. So it says parents don't need to maintain, but the children need to maintain. The children need to know their parents. Okay, and somehow this thing will work one way or the other, right? So in this case, the parents don't need a list, but the children need actually not a list, they need their parent name. So let's just think about this. Suppose you want to reach her, right? And I am the parent here. So you know that I'm your parent. You say, well, I want to send it to Salma, right? And so you send it to me, right? Now I think I probably need to know Salma, but anyway. So the thing is, um, somehow it will become clear as to how it works. But it says parent don't need to maintain assigned address table, um, which actually is little bit of a complication. We will go through the address assignment in a minute. The next slide, we'll talk about that. Link management. Each node maintains quality of the link to neighbors, and link quality is used as the link cost in the routing. What we do is when somebody is talking, they listen and they say, okay, like this guy's voice is very feeble, so he must be far away from me. Okay, let me understand the question. So you're saying children is just an API. Well, children is just your position in the tree. So if you're a child of somebody, then you know that everything you're connected to them, and so basically that is going towards the coordinator in some sense, right? Right. So that's what it is. Now I don't know what API means. Basically, if the node moves, they will have a different parent. If that's what you mean, right? I mean, they don't really the nodes don't create nodes; they just connect to nodes. See what I mean? So who you are connected to is your parent, and the devices move. So of course the parents will change, and we will talk about that too later on. Actually, link management. So right now the issue is we are going to do routing. If we are going to do routing, we have to have the link cost. And what is the link cost? Link cost is the quality. If something is very low quality, that means it has high cost. If something is very good quality, that means it is low cost, and I prefer to use that low quality. I'm sorry, high quality link. Frequency agility. Node experience interference report to channel manager, which then selects another channel. So basically, what you do is you talk and then you say, well, I'm getting 15% error rate. You tell the manager. So the network was using channel 2, let us say. And then the manager says, oh, 15%, that is too low. Let's try channel 3. And on channel 3, you get 10%. Oh, 10% is not good. So then you go to channel 4. So you find the best channel that has the lowest error rate. That is called frequency agility. Agility means we can change the channel as necessary. Okay. Multicast. And you don't have to packet to one person. You can send it to a multicast. You can say to all thermostats, to all light bulbs. Right? That's a multicast. Many to one routing. And in many cases, in IoT, really you're not trying to reach the device is trying to reach you. So there is a many to one routing. So you have 15 thermostats in your house. All of them are sending the temperature single place. That is called many to one. You might have sensors like door and window sensor. There are 15 windows in your house, all of them sending to one place, your security center. You have lights in your house, they all are connected to some control, right? So that is many to one. Asymmetric link. And each node has different transmit power and sensitivity, so path may be asymmetric. So let's say I am very high powered, you are very low powered, he is and maybe medium power, whatever. So when I send to you, I say the quality is good enough. You say the quality is good enough, I send it to you, but then you send it to him maybe because you don't have enough power to reach me. So that is the thing, asymmetric. The cost going this way is not the same as the cost coming this way, because cost coming this way is very high error rate, whereas the going there, the error rate is low and the cost is low. See what I mean? Mm-hmm. So the asymmetric routing, asymmetric link, fragmentation and reassembly, and then they allow the packets to be fragmented and reassembled. Now remember, 15.4 allows only 127 byte packet, so everything has to be fragmented. Pro feature, power management. Routers and coordinator use main power and devices use batteries. So basically things that have to be on, they generally are connected to the wall, and the other devices use batteries. Security standards and high. So you can have standard security or high security. And devices get new security code when they bake up, security key then when they bake up. So basically, so the security keys, we will go probably very briefly on the security issue. But if we change the security when you wake up, say suppose we had a key, and just like passwords, they could be changed periodically, right? So when you wake up, you may find that the key has changed, right? But you will be told that, okay, all right, using your old key, that this is our new key. And then you can have the new key. We already know these things, that there are what kind of devices? Coordinator. What does it do? I mean, I think I have finished all of this. I just want to, this is more like a test. What would a coordinator do? Yeah, timing is basically, remember the word time. So all the time is controlled by the coordinator, right? In this case, coordinator may also control the naming because it can control who gets how much address space. Okay, routers. What does the router do? Yeah, basically, yes, the answer is on there, but I really want to think about you to think about it, and then see, because we already talked about full function device. It can be a coordinator or a router. Reduced function device. It cannot be that, right? Zigbee Trust Center is the security keys and authentication. So there is a trust center which actually is keeps all the keys and things like that. So it says, okay, here is the key now. Here is the key now, right? So that is the trust center. That is kept under lock and key, right? If you have one. Zigbee gateway. Gateway is when you want to connect to something which is not Zigbee. So the hub that I have at my home is a gateway, right? Samsung hub that I have in my home is a gateway because now it can talk, all those devices can talk to non-Zigbee devices. Okay. Trust center is actually my hub. So in my case, it's not under lock and key. I said that, but basically the hub is very smart. I mean, it costs $70, so it has to be smart. It's the device, and so that is where all the keys are. I mean, and it decides when. And we said that there is a coordinator, which is the central point. Then the routers that transfer packets to other nodes, FFDs that are capable of being any of those two, and RFDs that only become a new leaf node. And then there's a trust center, which is where all the security keys are kept, and the gateway, which connects to other networks, right? So we will be using these terms from now on. And this picture shows some of these. So you can see this C is the coordinator. If you have very simple network, and that is actually most of the time the case, you have a central coordinator which really connects to all the leaves, and then the central coordinator can also become a gateway. Okay. Then the other possibilities are that your central coordinator has a router in between, and has many routers, or can have a complete mesh. So these topologies, while feasible, are rarely used. Most of the time it is a star or a star of stars. This is a star of stars, the middle one right here. Okay, everything is a star, and then this is a star of stars. And so these are devices, they require power, and C devices require power because they need to be doing more work than the E devices, which are just sleeping most of the time. Okay, so E's are all RFDs, right? Reduced function devices. Everything else is FFD. Yeah, everything has to be full function. If you are not a full function, you cannot be R or C. All right, the protocol stack, as they decided at that time, now this will change in a few minutes, but as they decided was that they will have their network layer, then they will have application support layer, and then applications. Okay, the applications are called application objects, and the support layer provides the common thing that all the applications needs, right? And so these Zigbee device object, GDO, actually is the control and management application objects. So all these objects are called GDO objects, right? And this is the management of GDO, and this is security. So the management and security are always on this side. Whenever we saw 7-layer diagram for networking, we put the security and the management on this side because you have to manage every layer and you have to secure every layer. right? So those are shown on the side. On the top of the Mac, we have network as expected. On the top of network, we have application support sublayer. I mean, you can imagine that this is similar to TCP plus session layer or something like that, actually. And then these are application objects. And GDO public interface, which is the for whatever reason you need the management, which is not private. So the application objects are called endpoints. Okay, and each physical device may have many applications, right? So it may have many endpoints. So for example, this is a switch, and one endpoint of this connects to the endpoint 6 of the light. Now light has many endpoints, and one connects to this switch, endpoint 6. So each of these end devices and node can have up to 250 application objects. So as you can see here, this is just one node, and it can have up to 256. Why 256? I mean 250 it says. Why 250? Because 8-bit numbering they might be using somewhere. So 250 application objects. And zigbee device object control and management of the application objects initializes the coordinator security service devices discovery. So this is the common program for the whole device, ZDO. And then application support services serves applications. Network layer does the route discovery and neighbor discovery. And we have a whole set of slides on this. So the network layer here does route discovery and the neighbor discovery. I mean, basically, before you can do route, you have to discover neighbors. You have to find out who can reach, and then who they can reach. That would be route, right? Basically, route. If I want to reach somebody far there, then you have to find out how do I go there. What is the optimal route to them, right? So that is route discovery. And neighbor discovery, just finding who you are connected to and what is their link quality. And GDO management and security service, which are on the side here. GDO management, and GDO is the whole object. So the reason it doesn't cover MAC and physical layer because they do not belong to the zigbee people. I mean, that really belongs to IEEE 15.4. And 15.4 has its own security and management. It's like if you're running on something on the Wi-Fi, so Wi-Fi will have its own security and management, and the rest of the stuff that is running will have its, okay. That's a good question. So, all right. So GDO is Zigbee device object. Okay. Each Zigbee device object can have many endpoints. Okay. An endpoint is the name of the application objects. Okay. So for example, a light might have a dimming endpoint, and some lights may not have dimming endpoints, and may have an on-off endpoint. Right? And so things like that. So there could be more than one endpoint to more than one application object inside a GDO, and therefore they call it endpoint. Application layer consists of application objects, also known as endpoints, and Zigbee device objects. 256 endpoint addresses, out of which 240 are applications. ZDO is AP0. Endpoint 241 to 54 are reserved. So they have 14 endpoints which are reserved, and 55 is broadcast. 255. So basically, as usual, when you have the address that 1111, that is 255, that goes to all objects. Otherwise, if you give a particular number and it goes to particular object, 0 is that GDO at the end, and then 1 to 240 are the other objects. Okay. Each endpoint has one application profile. For example, light on-off profile. Okay. Zigbee forum has defined a number of profiles. User can develop other profiles, and each profile requires a number of data items. Each data item is called an attribute and is assigned a 16-bit attribute ID by the Zigbee forum. So now that is another important thing is that, so each profile says the state is this and or the lightness, brightness is this. So suppose you want to define the brightness. Okay, so brightness is an attribute. Okay, and that number is given that whenever I say 5, that is brightness. Okay, and so they have defined a whole set of attributes which have a number, and then when you take a set of attributes, that becomes a profile. Clusters, a collection of attributes and commands on them is called a cluster. So now you take the attributes, and what can you do with those attributes, such as you can increase the brightness, decrease the brightness. Those are the only two I can think of right now. Two commands, and then that would become a cluster. Okay, commands could be read or written, read or write request or read or write responses. So that's fine. Basically, you can write an attribute when you say, okay, write brightness to 7. That's what you're saying is change brightness to 7. And read, find out what is the brightness right now. Cluster library. So they have a whole bunch of software which is called cluster library, a collection of clusters. Zigbee forum has defined a number of cluster libraries. Is a general cluster library, contains on, off, level, control, alarms, etc. Make a sound. That is an alarm, right? And so binding, a process of establishing a logical relationship. So binding is totally out of track here. Let me explain here is that binding is like this. Association, when you associate with somebody, that is when you are binding. So this R is a child of C, so when they get connected, that is binding. ZDO, this is the last point here, ZDO, Zigbee device object, uses device and service discovery commands to discover details about other devices, uses binding commands to bind and unbind endpoints, and uses network management commands for network discovery, route discovery, link quality indication, join and leave requests. So GDO is in some sense, I don't know. Some of these are related to the other layers, but this whole common application object that they put together does the things that we said, the other layers might also do. So uses network management commands for network discovery, route discovery, link quality indication, join and leave request, binding commands, unbinding commands, and so on and so forth. So all of this software, which is common for all these layers, has been put here in this video. All right, so the profiles are smart energy profiles. For example, electrical, gas, water meter reading that follows the electric energy profile. Commercial building automation, smoke detectors, lights, they follow basically profile. Home automation profiles, there are profiles for remote controlling lightings, heatings, doors, monitoring blood pressure, heart rate, for the health, telegram phone profile, and so on and so forth. So there are many of them. And there is a remote control profile, which actually I put a whole new slide on, but anyway, I can talk about it here, is that you can also use Zigbee for remote control. And many of the devices that you are remote controlling at home might be using Zigbee right now. Okay. And particularly if they're not line of sight. For example, in my home, when I control my DVR from dish, I can do it from any room far away, even out of sight. And that is obviously wireless Zigbee. You can also use Wi-Fi for that, but Zigbee has done this one extra step where they worked with the RFCE, Radio Frequency for Consumer Electronics Alliance, for remote control. So Wi-Fi may not have done that. So, so that's why zigbee might be more likely. And then industrial monitoring control, temperature control, pressure control, position, and many others. So there are lots of profiles. Huh? In case of which one are you talking about? RFCE? Are you talking about which one? Huh? All general Zigbee applications. You're saying it has less limitation? Yeah, okay. So Wi-Fi has nothing specific to any application, right? I mean, it has many variations for high throughput, this and that, and real time, but it doesn't define the profiles. It doesn't really limit the applications. Bluetooth, because the devices are very small and they didn't want to have, them trying to negotiate every possible thing, they set a very limited set. And so does the Zigbee. However, I mean, both of them are realizing that those are limiting in some sense. Okay, so as you will see, they are getting away from that slowly. But this is what this is what it is that they're limited to these profiles. Okay, and here is a list which is available right now. I mean, on Amazon, I just copied these devices. These are all Zigbee devices. You can buy a lock, you can buy a light bulb, hub, motion detector, outlet, temperature sensors. These are all Zigbee devices. And of course, I mean, if you want to talk to them by Wi-Fi, you can talk to them, but you will have to go through the hub. Hub is the gateway. Now we go into some theoretical concepts. And first concept is, how do you assign address to your children? So each node gets a unique 16-bit address. All right. So the address is how long? First, your global address is 64-bit, but since that is too big, particularly our packets have only 127 bytes, so we give everybody a short name 16-bit. And so each node gets their own address. Now they can give it to their children two ways. One is by distributed method. So this is what we are talking about, the distributed method. And second is a stochastic, just randomly. So this distributed scheme works for the tree architecture, tree structure. If you have a simple tree, which we call a star actually, if you have a simple tree, you can use this scheme that I'm going to talk about. It looks very mathematical, but it's not that difficult. Each child is allocated a sub-range of addresses. So as I said, that we give you a sub-range, 0 through 10, 10 to 20, 20 to 30, something like that. And then you can have that many children. Need to have maximum depth L, need to limit the maximum depth. Now these children can have children too, right? So they say maximum L is the depth. Maximum number of children per parent is C. So you cannot have more than C. Maximum number of routers is R. Okay. So you can imagine this particular, let's see, this particular thing here, where you have children of children, right in the middle here, star of stars. So you can see what is the maximum level down and how many routers maximum and how many children maximum per parent, right? So we will take an example and be more clear, but that's what it is. C is the number of children, R is the number of routers, and maximum depth is L. If that is the case, then the address of the nth child would be parent plus n minus 1 times SD, where SD is this formula. Okay, now that formula looks complicated, but we will apply it one by one, and then it will turn out it's not really that difficult. But so here's an example, and listen carefully because this is also a homework. Okay, so basically this is a star core center coordinator. It has 4 children, 4 routers, and then they have some number of children. So the maximum level we have done is 2. Okay, And we have said that there won't be any more than 4 routers, so 4 routers. All right. And nobody will have any more than 3 children, that we just decided. Okay. So L is equal to 2, R is equal to 4, C is equal to 3. Now, D is the depth. For the coordinator, the depth is 0. For the routers, the depth is 1. And for these leaves, the depth is 2. All right. So for the coordinator, what we do is D equal to 0. We just calculate S0, C times R raised to L minus D minus 1 minus C plus R upon R minus 1, and so on and so forth, right? Put all the numbers together, you get 4. So S0 is 4. Basically, what that means is that as the coordinator takes an address, let's say 1, and it will give 11 to R1 and then 15 to R2. Why 15? Because it has to give a gap of 4 for each of its children. Okay, so R1 is 10 plus 1, R2 is 10 plus 1 plus S0, R3 is 10 plus 1 plus, and so on and so forth. So now what we have is 10, 11, 15, 19, and 23. This much is decided by putting into that formula. Now, what do these guys do? The router says, I am at depth 1, and therefore S1, they calculate S1, and after putting all this C, R, L, D, and all that, it comes out 1. So their children will have numbers which are separated by 1. Okay, so this will give it 12, first child, 13, and 14 if it comes up. Right now there's no 14, but it just reserves that one. This one will have, this has 15, so this will give 16, 17, and this is 18, and so on and so forth. So you can see there is no duplication, and everything is properly divided in this kind of, what I would say is very symmetric star. I'm saying symmetric because everybody has the same number of children, everybody has the same number of parents, and blah, 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 which is, so now this is very limiting because you never know how many children where and this and that, and trees might not be identical. So this actually was the original scheme, and it didn't work out that well. But since this was the original scheme, you got to just learn it and do it in the homework. Okay. Okay, there's a mistake. So this will be R1, R2, R3, R4. So this stochastic one works out better now because you don't have to limit anything, neither the level nor the, anything like that. You just draw a random number and see if somebody else has that name in the tree. If nobody has that name, then you just stick. If somebody has a name, then you just draw another random number. So that is what it is. Parents draw a 16-bit random number between 0 and 2 raised to 16 minus 1, which is the maximum possible number, right? For 16-bit, all ones would be this one. And they assign to a child, a new number is drawn if the result is all 0. If you get a null, of course, you have to draw another number because 0 is not a good number. Or if you get all 1, that is not a good number because all 1 means to everybody. And so assign that number, and parent advertises the number to the network. If another node has that address, repeat, otherwise. So this simple scheme actually works out better than any of that formula thing, Now zigbee routing, and this is another little bit mathematical, is that there are basically zigbee is what we call a mesh network. And for the mesh network, the academics and people have done a lot of literature how to do routing, and there are two of them which are very popular, AODV and DSR. Okay, and then there are two others, pre-hierarchical and many-to-one. So we will talk about AODV first. AODV stands for ad hoc, on-demand, distance vector routing. All right. So ad hoc, we know what it means. Ad hoc means that there is no infrastructure, and I mean that's what it is, right? On demand means as whenever we need it, we get the route. Otherwise, if we don't need it, we don't get the route. Distance vector. Now, this is something that I expect people to know from the previous course. Does anybody know what distance vector means? 473. So they didn't teach you enough computer networking. Because if they teach you routing at all, then they teach you that there are two ways to do it: distance vector and link state. Okay, OSPF is link state, and before that we had distance vector. So basically, this one uses distance vector. AODV uses distance vector, and it will become clear in a minute. In link state, what you do is you advertise to the world your neighbors. So you tell the world that I have 4 neighbors and the quality is good, bad, whatever to each neighbor. This is the cost. Right? You tell to the whole world. That is link state. Other one is distance vector, where you tell your neighbors your table. You tell that, look, here's my table, and if I want to go to this one, then this is the distance, and here's my table. If you want to go to this whole world, so big table, I give it to 4 people, right? So there are two choices. Either you give a small table, which is 4 people to 100 people in the world, or you give a 100 people table to 4 people in the world, right? And so those are the two methods. So this is distance vector. Distance vector means I'm going to tell my neighbors only about what my big table looks like. On demand means reactive. Reactive means you don't create the table until you have packet to. So I'm not going to just, like in IP, what they do is SPF. Everybody knows the whole routing table for everybody. But here the table is changing so fast that if you kept track of everybody, then you'd not be doing any work. Just keeping track of people, right? You just keep track of people that you need to contact. Because this is called reactive, as opposed to proactive. Proactive means you do it before you need anything done. Avoids unnecessary computation if there is no traffic, which is the case. Generally, there is no traffic. Source broadcast route request. So there is something called RREQ, RREC. RREC, the source says to all its neighbors containing source, destination, and broadcast ID. So what the source does is it sends a passage like this, a message which will go in a minute. This is called RREC, route request. So it sends a RREC to all the neighbors and say, hey, I'm looking for somebody. I mean, right now we have very small networks. I can't give a big example, but let's say there was a second row of people sitting there. So I will tell 4 people that, okay, I'm looking for Mr. X, and Mr. X is sitting over there. Then it will take some time to find him, right? But here, so basically, so that's what we do. We send an RREC. Each node determines if this is a new request or this is an old request. So, I mean, because the request is broadcast and broadcast and broadcast. So I send it to you, you send it to your friend, you send it to your friend. To the whole world, you will get many copies, right? The first thing you see is whether it is a new request or is an old request that came back to you. You had just sent it to your neighbor and your neighbor sent it back to you, right? So you get rid of all the duplicates. Then, if you have an answer, then you get a reply, right? If you know what we are looking for, then you create a reply. So yes, it makes a reverse route entry for the source. Now here is what it does, okay? If this is a new request and this copy has a lower cost, then you make a reverse route entry for the source in its table. So this is this is important part to understand. When I send you request and you get it, right? And it turns out that, so now you know that how far you are from me, because you got it first, and it does have in it, how long did it take to get to you. And this was the first copy you got it, so means if you wanted to come to me, this is the shortest path, right? So reverse path. Although you are not looking for me and I'm not looking for you, I'm looking for somebody else. But everybody on the way can learn about me, right? Now that request will come back to you after some other people, but now you're not going to make any note because this is duplicate, right? Very first time when it comes, that time you make a reverse route entry. Reverse route means going back to the source. Clear? No, the copy will not have even shorter because copy will always have longer. You don't even have to look at it because if you already heard it before, if it was shorter, then it would have come first, right? Whatever path it came by, if it came first, that is the fastest. All right, so the optimal reverse path. The node then it checks if it has a route to the destination. If yes, it sends a route reply. So, okay. When the source receives a route reply, it selects the lowest cost path and sends the packet. So when you get the reply, then I know how to send it. A node cannot forward the packet, it sends a route error. So basically, the packets basically now will be sent on the path that I determined. Now it is quite possible that in the meantime somebody moves, not that destination, but somebody moves, and that path is no good, right? In that case, you send it along that path, and it will come back to me saying, "Now, sorry, this is no longer good." So then you reinitiate the discovery. Now, how is it done? So we will see. Look at the messages. So routing table path is not stored, only next hop is stored. So the routing table consists like this. To go to 10, where 10 is somewhere there, the destination, the next node is number 2. Okay? And the sequence number is the timestamp. And this answer was good at 10 o'clock. Rather than saying 10 o'clock, this answer was good up to number 10. Okay? And every time I send a request, it will become 11, 12, 13. So up to time 10 equal to 10. T is really not a time, but it is a time stamp, sequence number. Up to that time, the next node was that. So route discovery is you flood a RREC, where RREC is like this. RREC has the source address, request ID. Request ID is basically sequence number. Okay, so when I send a request, I send request number 1, request number 2, request number 3, like that. Okay. Destination address is the node 10 that we are looking for. Source sequence number. So what source says is that in my table, I already have, now I'm using number 10 too many times. So let's say I already have 7 o'clock answer. So 7. My sequence number is 7. I'm looking for something better than 7. 7 o'clock, I know the path, but I don't know after 7 o'clock what happened. So this is the source sequence number. Okay. The destination sequence number, sequence is the clock counter when the source sequence number is the when the this is just the time for me right now, and the destination sequence number is the number that I have in my table. Okay, the 7 will be here in the destination. But in my table, I already have answer up to 7. Right now my time is 10 or 11, whatever, right? And I'm looking for that address. So now let's just go over all the fields. Okay, hop count. Now hop count is in the message. So this basically says how far the message has come. When I send it, maybe hop count is 0, then it becomes 1, 2, 3. As it changes at every hop, the nodes increase the hop. Clear? Okay, so now let's look at the 5 or 6 fields here. Source address is my address. I'm sending the request. Request ID is my ID number, and just sequentially increased every time. destination address is who I'm looking for, source sequence number is my current time, and the destination sequence number is what I have in table, and hop count is initialized to 0 first. Now, as it goes to the nodes, they can either reply to rrec only if they have a route with a higher destination sequence number. What that means is, so I know 7 o'clock time route, right? If you have an 8 o'clock route, then you can reply. But if you have a 6 o'clock route, don't even bother. Right? So how you do that thing? By looking at the destination sequence number in the message and in your table. Clear? In the message, the source has put a destination sequence number. That is the time that it knew. And you have in your own table the destination sequence number. You compare the two. And if you have a better answer, then you reply. So this is our rep. Okay, route reply. What the route reply will consist of is the source address, destination address, destination sequence number, hop count, and lifetime. Okay, so now let us see one by one. Source address is who is sending this, right? So I'm sending it. Suppose you are sending it, this will be your address. Destination address, who is it going to? Generally, you will be sending it back to me. So this will be my address. Destination sequence number is for number 10, the packet number, the destination number 10 that you were looking for, and the hop count, my hop count is 5 in my table, and lifetime. Now the lifetime is how long is it good for, and I don't have any indication here as to how do you get that. But anyway, so this answer is good for next 1 hour, 2 hour, 3 hour. But the old entries are no good, right? Even if you have a better answer, but if it is very old. So the destination sequence number is from the destinations counter. Lifetime indicates how long the route is valid. Intermediate nodes record the node from both rrep and rrec if it has a lower cost path. So this is important. And let's make sure that we understand this thing. So when the requests were going, we were making note of the source. Now the replies are coming. Okay, the replies are coming. Then if I have in my table that the number 10 is 10 hops away at 7 o'clock, and now this answer is at 8 o'clock. If it is better, then I will write it down. Right? So I can update my table. Even though I don't need it, I'm going to update my table from rrep. So intermediate nodes record the node from both rrep and rrec if it has a lower cost path. So the reverse path. Okay. Backwards route, and we can also record for the source address as well. So for both. Backward route to destination is recorded if sequence number is higher. So both things are recorded. We record the source address and we record the destination address. If it is a better path to the destination, we record that, and if it is the first answer, then we record that. Old entries are timed out. AODV supports only symmetric links. Symmetric means the cast this way is same as cast backwards. So if you get something fast, you assume that you will be able to get along that path fast. If it was asymmetric, then this will not work, because you can get something fast from me, but if you're sending it this way, it will be very slow, right? So this will not work for asymmetry. All right. So now we do have to go through a numeric real example, and please listen carefully. And now this gives me, again, this is homework as well. So let's say node 1 wants to get a route to node 10. Here is node 1 on this corner left, and then node 10. It wants to find out what is the shortest path. So node 1 will send it to all its neighbor, 2, 3, 4. What is request says? I need a request, so I need a route to 10, which is fresher than 1. This is my destination sequence number. So I have 1 o'clock answer, but I need something better than. And this is my broadcast number 1. This is my request number 1. Okay, the node just wake up, so everything is 1. Generally, the broadcast number would be the sequence number. And the destination sequence number is whatever answer I already have. So node 1 will send to 2, 3, 4. 2 will send it to 1, 5, 7. 2 will send it to 1, 5, and 7. And 3 will send it to 1 and 5, and 4 will send it to 1, 6. Everybody sends to their neighbors. Now 1, when it gets this request that 1 is looking for 10, it says, hey, come on. this is I already sent that one a minute ago, right? So it will throw that away. So 1 will throw away how many messages? 3 messages coming back. And so 5 and 7. Now what 7 will do, it will send the request back to 2 and 9. 5 will send it to 9 and 8. Now 2 and 3 say, hey, we have seen this before, right? And so they will drop that, but 8 and 9 will keep it. 4 will send it to 6 and 1. 6 will keep it, and 6 will send it to 4 and 8. 4 will drop it, 8 will keep it. 8 will actually also drop it, possibly, because it depends on when it comes. This is 3 hops, this is 3 hops, this is 3 hops. Whichever makes it first, yeah. Is there a direction? No. There's no direction, there's no arrow here. Basically, everybody is saying, if there was an arrow, then you don't have to go backwards. Right. Yeah, there's no arrow here. In this diagram, there's no arrow. Yeah. Yeah, 5 will send it to 2, 3, and 8 and 9. Yeah. To 3 and 2. You can see it in a picture, but I mean, I don't think you can, when you get a message, you can figure out who is left and who is right. Right? So the only way you can figure out that this is old is because the sequence number is there, right? I mean, right? So here is the whole table, by the way. I made this table using Excel, and this is not from any book. So basically, this is the only place you will find it. And you have to prepare a similar table in the homework, which is coming right after this. Okay, so I'm going to read it line by line. So 1 out of 1 sends a message which says this message is from 1. And the message is 1. It is going from 1 to 2. Is not. This doesn't say in the message. This is an rrec. In the rrec, the ID is 1. Okay. The source sequence number is 1. Destination sequence number is 1, and the hop is 1. And this is a new. So basically, the destination is 2, right? The XN at the recipient. What 2 says, oh, this is a new request, so I got to broadcast to everybody, right? And what it does is, in its own table, it says that, okay, I have seen a request which was where somebody was looking for 1 with a sequence number 1, and hop was 1, and it came from 1. Okay, this next is important. Next means the previous guy who sent it to me was 1. So what it has done is it has recorded this path. It says if I ever want to go to 1, this one, I will follow this particular link, right? Now, 2, then, sorry, from 1 to 2. 1 to 3, same thing happened. 1 to 4, same things happen. Now, these tables are at different locations. This is the table at 2, this is the table at 3, this is the table at 4. Now what happens? 2 sends it to 1. Right? 2 sends it to 1. In that request, everything else is as before except the hop count has gone to 2. right? Now, when one receives it, it says, hey, I have already in my table this thing. So it discards it, nothing changes anywhere. 2 sends it to 7, 2 sends it to 7, and now at 7, a note is made that this hop is 2. See, the hop number is 2 here. And if I ever want to go to 2, this is the link to follow. 3 sends to 1, and it's a duplicate. Sorry, 2 sends to 7, 2 sends to 5. So 5 also makes a note, right? 3 sends to 1 and 5, both are duplicate. It is discarded at 1 and discarded at 5. 4 sends to 1 and 6, both are duplicates. No, sorry, 6 is not duplicate. 1 is duplicate, 6 is some note is made for 4. Are you following that? Okay. Now, then 7 sends to 2 and 9, 5 sends to 3 and 2 and 9 and 8, 6 sends to 4 and 8, and 9 sends to 8 and 5 and 7 and 10. All right. Most of these are duplicates except, here. When 5 sends to 8, that's the new thing. Okay. Now, are you following up to here? 9 to 10. So 9 sends the request to 10. Then something new is going to happen. But before I go to that line, is this part of the table clear? Eh? 9 sends to 7, it's a duplicate. 9 goes to 7. It's not sorry. Okay. So that's a good one. Let's see. Maybe that I should have said new RR request. Let's just double check. 7 did get before here. Right? So this is a duplicate, and therefore this will be 0. Duplicate ID, discard. Yeah, unless it is a new thing, you don't even look at it. So this should all be blank. Now, what happens when 10 gets it? What happens at 10? 10 knows the shortest path. Right? So 10 says, hey, this is a new request. Not only I need to make something in my table, which it makes it. So it says that if I want to reach 9, this is the path. Right? And for 1, actually, so what it is saying is basically if I ever want to reach 1, the fastest path is through 9, and it is 4 hops, and the sequence number is 1. Right? Fastest path to 1 is through 9. And it responds. So now, before I go to that rep, some more packets are going to fly by. 8 is going to 6, 5, and 9, and they will all be discarded. Right? Now, 10 is going to send it back to 9. Now, 10 is not going to broadcast the reply. Okay? Now, 10 says, I need to send this reply to 1. Right? And it knows the fastest path to 1. That is through 9. Right? So it sends a packet just to 9 saying that here is our rep. Okay. Your request ID was 1. The source sequence number was 1. The destination sequence is 6. Okay, so my time is 6 now. If you counted the time here, you will find out this is 6 times have gone up, right? And now, it initializes the hop to 1. Basically, we are beginning again. Now, this will be counted backwards. Now, so So now what 9 will see, 9 will say, oh, this is a new R rep. This is the action at the destination, at the recipient. So it will make a note of the in the table and forward where it will forward. Now, before we go to where it will forward, let's see what it does. It is in tone table. It says that if I ever want to reach 10, the fastest path is through 10, I mean through this one neighbor. And so this is the entry simply for 10, right? But then it already has an entry for 1 here. Entry for 1 where the first time it receives for 9. So 9 is right here. So it says I have to send it to 7, right? So 9 sends to 7. And then 7 says, how do I send it to? I mean, it also makes a note of 9, path to 9, but it sends it back to 2 because that is where it first learned of 1. And 2 sends it to 1. So when it comes back to 1, one knows that the fastest path to 10 is through 2, and it is 4 hops away. Look at this table. So what one has learned is that the fastest path is through 2, and it is 4 hops away. Okay. Okay, because, okay, let's see. So the in the very first time, these 3 packets were the sequence number. I mean, basically time was 1, right? Now, by the time the packet reaches there, so let's see how the packet reached. It reached from, let's see, it reached from 9. Actually, it probably reached from 1259, right? So if the time was 1 here, it was 2 here, it was 3 here, it was 4 here, it was 5 here, and then the answer was 6 there. I think that's what 6 is basically. It started with 1, and then became 2, 3, 4, 5, and then 6 is the written backwards. Any other question? Yeah, right. Okay. So this one is showing packet number in and packet number out. 3, 4, 5, 6, 7, 8, 9, 10, 11. This is just a sequence number. And what this is showing, this is a pointer to which packet we are talking about. So this packet was sent from 1 to 2. And so this ended up on this line. In this line, it is going from 2 to some other place. The same packet is going from 2 to 7. The same packet is going from 2 to 8. So this is simply indicating which packet number. So this is basically link, right? I mean, just on this table, this is not maintained anywhere. But for you to understand where this row came from, this row of the entry, this is packet number 1 that came to 2. And when did it come? It came here. Right? Let me take another example. This one, this is packet number 2, which came to 3. When did it come? Packet number 2 came to 3 right here. This is packet number 2. It came to 3 right here. This is packet number 3 came to 4. So 3 is here, came to 4. And now it became 9, right? And then 9 will show up at 1, wherever. I mean, 9 doesn't show up because it is discarded. But if so, this is sequence number. This is just a packet number, so that we know row number, second column. And the first column is just pointing out where are we in this, this which packet we are talking about. Because by the time you are here on the 4th row, you have 3 packets to handle. Right? So which packet to handle first? So this column makes it easy to keep track of everything. Yeah, actually, yeah. See, the thing is, out is the just packet number. See, here's this is the table I made it. Okay, let me tell you, I could have made it so that the out is in the first column. So then you know the sequence number, right? In is basically where that packet number ended up, right? And so this packet number 1 ended up at 2, but then it became 3 copies, 4, 5, and 6. You understand? The packet number 1 became 3 copies because it was sent to 4, 5, and 6, right? I mean, it was sent to 1, 7, and 5. Packet number 4 was sent to 1, packet number 5 was sent to 7, and packet number 6 was sent to 5. All right. Now, most of these might be dropped, but some might continue. So let's say 2 was dropped at both places, 3 were dropped, but let's say this one. 10 was forwarded, right? And the 10 will appear here. But by the time you get to 10, if you don't keep these numbers, then you will not be able to keep track of what happened to everything up to 10. Right? So first what you do is you keep track of these, and then make sure that I mean, one of these could be also be called. I mean, actually, you probably may not need these first 2 columns. You can just do it from here, but make sure that you don't lose something on the way. All right. So basically, before I go too further, I mean, the homework is here, and I just want to make sure that I mean, homework is at the end, but that is due now. Okay, homework 10B actually, because 10A is the homework related to that sequence numbers, the addressing, that formula S raised to D and all that business, and homework 10B is AODV. All right. So look at the homework and see if you have any questions about it. Yeah.
So in packet 22 it reaches to
packet number 2, yeah, 10, 22 reaches the destination. No, I'm not continuing the request. The nodes don't know that something has reached the destination, so 8 will continue. So the thing is, I mean, 8 will continue, and we got to just make sure that we have taken care of that, right? I mean, I could have just put this 10 right there, where the 10 responds now right away when it got the answer. But what is happening is that, I mean, just to make sure that everything is reached final place. And in fact, I mean, some of it might even continue even beyond this, because I mean, it so happens that the 10 will not really send back anything, and everybody else has sent everything in every direction. So everybody is all set. So at this point, after 25, nobody is basically going to do anything more. So then we start the backward direction. And this is just a packet numbering. This is nothing. This is not time. This is the packet numbering. So if you want to look at the time, you really look at this column here. So this is everything here happens in the first slot of time, where half is 1. Everything else here happens in the second slot of time. Everything else here happens in the third slot of time. Everything else here happens in the fourth slot of time. In the fourth slot of time, 8 is going to send these packets. Right? So let's finish the fourth slot of time before we go to the fifth slot of time, where the 10 will start. Answering something like that, right? So this action, basically, this is the only time when the action completes. Now we go to 10 to 9, 9 to 7, 7 to 2, 2 to 1. Okay, that's a good question. As to but it just so happens that the 9 was, we put 9 first and we put 8 second, and but we have to put all of them.